Page 50, section 1.4. We don't really have a handout for this because this entire section is about graphing calculators and graphing calculator skills. So we're just going to go through numerous examples together on the calculator. I did, however, put in your notes packet a couple of typed pages. That sheet that I gave you, that handout, comes from College Board from AP Central. And basically it's a handout called Lies My Calculator Told Me. It's a series of things that your calculator does not handle correctly, and it literally will give you the complete wrong answer. Most of the things on that sheet we don't understand right now, so we will go back through it again when we get close to the AP exam and we're reviewing for the AP exam. There are a couple of things on there that will make sense to us, and we'll catch those as we're going through today, kind of mixed in with these other examples that we're doing. All right, so page 50. First thing that we want to be sure that we can do on a graphing calculator is set an appropriate viewing window. And so we're talking about the display window or the viewing screen or the viewing rectangle, all of those bold print terms there on page 50. What they're talking about is an appropriate viewing rectangle. So for instance, if we had the equation, let me clear this stuff out of here. If we had the equation y equals x squared plus 11. When I graph, I typically start with a zoom standard. Remember, we've got several different zooms that are kind of our defaults that we go to all the time. But the zoom standard, zoom number 6, is the one that's pretty much tens all the way around. So when you draw that out, it's going to go 0 to 10, 0 to negative 10, up 0 to 10, and down 0 to 10. Okay, so it's kind of like a standard all the way around. How come it's not graphing anything? My stupid calculator, what's wrong with it? Usually when there's something wrong with my stupid calculator, it's operator error, right? What does y squared plus 11 look like? First off, what does y equals x squared look like? Parabola opens up. What is the plus 11 causing? A y-intercept of positive 11, a vertical shift up 11 units. That's why there's nothing showing up on my screen. There's nothing wrong with my stupid calculator. So I need to go back, and I can't just use perhaps the default. I need to go back and just manually set an appropriate viewing window. So do I need to change my x values? No, they're pretty much, there wasn't a problem with them. It was that I couldn't see the y values, right? So I'm going to scroll down here to y. There was nothing to be seen between negative 10 and positive 10, so I'm going to get rid of that and tell it to make my minimum value now positive 10. And typically if I'm seeing 20 units vertically, I could just change this to tell it go 10 to 30, and I could still see those 20 units vertically. So now when I go back to graph, now I'm actually getting a good image of that parabola. All right, look at another one. Let's say that we have y equals x squared plus 3, example number 1 in our textbook. For y equals x squared plus 3, they give me 4 different viewing rectangles there to choose from. Okay, so in the textbook, when they give you something like, if you look at the C option, they're in example 1 on page 50. The C option says bracket negative 10, comma 10 bracket by bracket negative 5, comma 30 bracket. All right, what that is that you're looking at is the first set that they give you are your x values that they want you to use. So like that negative 10 is your x minimum, the positive 10 is your x maximum. By the second set of bracket, the second bracket they give you there, those are what they want you to use for y. So the negative 5 is your y minimum, and the 30 is your y maximum. All right, so let's put those in. they give me here A, B, C, and D. Let's put in those 4 different sets of viewing rectangles and see which one is the best fit for our graph. So the first one that they give me, they told me to go from -2 to 2. And same thing on my y values, to go from -2 to 2. So if I graph that, is that a good viewing rectangle for that graph? No, I don't have anything there. So let's try B. For B, they told me to go -4 to 4 for x and y. All right, well, that's better. At least I have something showing up on my graph, right? But it kind of makes me think that I have a smiley face instead of a parabola. So that's better than the last one I had. We'll see what other options they give me. So go to the third one. That was the one that we discussed previously. The -10 to 10 for x and the -5 to 30 for y. All right, that looks pretty promising, right? Is that better than the last one that we had? Yeah, so far that's our winner. So let's try the last one they gave us, because maybe the last one they give us is even better. So the last one that they give me is -50 to 50 and -100 to 1,000. Gracious. All right, so if I graph that one, which is better, the last one we had or this one? The last one. How come?
Because you can see the vertex.
Yeah, for the last one, we were able to see that we had a y-intercept at +3. This one looks like my y-intercept is at 0, right? So definitely that last one would have been the best viewing rectangle for what we had. All right, go to the next example. For example number 2, they ask us to determine an appropriate viewing window for the square root of 8 minus 2x squared. So square root of 8 minus 2x squared. Missed my x. Square root of 8 minus 2x squared. So again, I kind of tend to start with a zoom 6. It's kind of like my standard viewing rectangle. So looking at that, it kind of gives me the idea that maybe it's a semicircle. Not really sure. It might be a little bit easier if I zoomed in and got a better look at it. So maybe I did a zoom 4 or something like that. There is a zoom on your calculator that I have never taught you to use. And the only time that I think it would be appropriate to teach you to use it is on the lesson Lies My Calculator Told Me. There is a button on your calculator called Zoom Fit. And the idea of Zoom Fit is you're supposed to be able to put in an equation and hit that zoom, and it will fit the window for you that would be appropriate for that graph. Okay, well, let's try that on this one. I'm going to choose Zoom Fit, and if I do that, this is the graph that it's given me. This is what it says is an accurate depiction of the square root of 8 minus 2x squared. I may not know exactly what that graph looks like just yet, but I definitely know that that's not appropriate. Look what it did for the window. It's got the x values going from -10 to 10. It's got the y values going from 0.8 to 2.8. So basically, when I go back and look at that graph, the whole y-axis is only 2 units long, where the whole x-axis is 20 units long. Of course that thing is not going to be an accurate depiction when the little tick marks that are in between the graph, I mean, like, you know, this is 1 unit here, whereas this is 1 unit over here. That's not going to give me an appropriate graph. So Zoom Fit is the best way to get your calculator to tell you a lie for what a graph looks like. So let's go back to maybe zoom 4. A little closer up version. And that's giving me a better depiction. And sure enough, if you'll notice, see how my tick marks are getting closer to being the appropriate width where they would be about the same. We do have a zoom on our calculator that will square those off and make them the exact same distance apart, and that is our zoom square. So if I choose zoom 5, then it does go back and it makes each of those the same width, and I do get an accurate depiction then of what that. All right, so look at the next one, example 3. It says graph the function y is equal to x cubed minus 49x. Y is equal to x cubed minus 49x. And again, they want us to choose an appropriate viewing window. So again, I'm typically going to start with a zoom 6 just to see what that gives me. And I get 3 vertical lines. I know that is not what that graph looks like. So here's where I have to put my calculator and my knowledge of calculus together. If I'm looking at y equals x cubed, right, we know that when you've got a positive leading coefficient, the graph is going to end going up. And we know if it's a degree of 3, it's going to have 2 turns, right? So I know the basic shape of that graph. So then when I look at this picture, I can interpret it a little bit better and go, oh, okay, I understand. Basically what's happening here is here's the part of the parabola where I'm going up. Here's the part of the parabola, or the, I'm sorry, not the parabola, the cubic where I'm going up, and then it's going to turn and come back down, and then it's going to turn and go back up again. All right? So, do I need to change my x values? They look pretty good. Do I need to change my y values? Absolutely. So, let's go into window. And I'm going to leave my x values the same. What do you want to use for your y values? There's not a right or wrong answer here. This is completely arbitrary. It's just trial and error. So, what do you want to try? Okay. 100 and negative 100, really? We got to that extreme? That's not going to skew my graph? So you might look at it and the first thing you might try is negative 20 and positive 20. And it doesn't get you anywhere. So maybe you go negative 50, positive 50, and you're only halfway there. And so then maybe you do go negative 100 and positive 100. And that gets you almost there. By the way, just for funsies, let me go back to zoom 6 for just a second. Watch this. I'm going to go to that zoom fit again, you know, the thing that makes the perfect viewing rectangle for me every single time without me having to think about it, right? Well, yeah, that gave me a good picture of a cubic. Look at your window. That's not an appropriate, that's not the best window for this graph. Somebody last period, after we played with it a little bit, they hit zoom fit. I think they had already changed it to like 100 and negative 100, and they hit zoom fit, and it took them to 2 million and negative 2 million for their y values. That definitely would not be the best viewing rectangle for our graph. So we had decided that the x values were fine. When we did negative 100 and positive 100, we were almost there, right? Definitely by the time I go to maybe 125 or 150, that should cover it. I don't need to be going to an extreme of 510. So 125 almost got me there. If I go back to 150, then I should have it. So again, there's not a definitive right and wrong answer here. I may have chosen 150, you may have chosen 175 or 200 or, you know, something like that. We just want to be sure that we're getting a clear and accurate representation of our graph without extremely elevated values that aren't necessary. All right, look at example 4. example 4 is similar to one of the questions that they gave you in the handout. And one of the times that you're going to have to be most on guard is when you're working with trig functions that have had amplitude, period changes, that type of thing. All right, so if I'm graphing sine 50x, first off, do I need to be in degree or radian mode? Radian mode, right? And we do have a zoom that we used a lot for trigonometry that was really helpful. Zoom number 7 is zoom trig. Well, I don't know why you think that my calculator can't handle this. I mean, that looks like a fabulous graph. Yeah, it does, but that is absolutely nothing like what this graph actually looks like. That is a flat out lie my calculator told me. Because what does that 50 in between the sine and x do? What does it cause? A period change, yes. It causes a horizontal shrink by a factor of 50. If you take your sweet little sine curve and you shrink it by a factor of 50, it does not look like the pretty little graph that we have on our calculator screen right now, right? So in actuality, there should be 50 of these curves in the same amount of space that I normally put one, but it just overflows my calculator and it just goes through and does the best that it can. If I want an accurate picture, then I'm going to need to go manually set a window, and I'm going to need to create a new period to do that. So what is my new period going to be? New period is always the original period divided by the b value, right? So what's the original period? 2 pi, and what's the b value? 50. So I could reduce that to pi over 25, right? My new period would be pi over 25. So if you want to see 2 complete cycles of that, you could just tell your calculator to go from negative pi divided by 25 to positive pi divided by 25. And it will change the value for you. It's not going to leave it as that. It's going to change it to a decimal approximation. That's fine. Now that is an accurate representation of what that graph looks like. All right, look over at example 6. Example 6, we've got y is equal to 1 divided by 1 minus x. So clear this guy out. We've got y is equal to 1 divided by 1 minus x. And again, just by default, I usually start with a zoom 6. That's that standard with the 10s all the way around. Okay, how many of you, when this came up on your calculator screen, how many of you have a line running right here? Almost looks like it's graphing the asymptote there. How many of you have a line there? Okay, I've got a couple of you, 2, 3, maybe. There doesn't seem to be any rhyme or reason to this, why sometimes it'll put the line there and sometimes it won't. What it's doing is when it graphs, it connects the points that it finds. So what happens is when it has a point up here and then it has another point down here, it tries to connect them. And so literally it's not trying to show you there's an asymptote there. It's literally drawing a line as part of that graph. So those of you that have that line on your screen, and like I said, there doesn't seem to be a rhyme or reason, like sometimes it pops up and sometimes it doesn't. A way that if you're working on a problem and you're not sure whether there's really a line there or not and you want to be definitively sure, one thing that will usually help with that is if you go to your mode, and we usually leave our calculator in connected mode because we do want it to play dot to dot and connect the dots, right? But if I would switch it over to dot mode, then when I go back to that graph, it doesn't connect the dots. Like it just plots the points, but it doesn't connect the points once it plots them. So that would take care of, for those of you that you were getting a line running here, when you switch it to connect from connected to dot, does that make that line go away? That should fix that problem for you. Okay. So again, if you run into a scenario, I'm going to go ahead and switch this back now, but if you run into a scenario where you have a line and you don't really think there should be a line there and you think your calculator might be misleading you, that's usually a way to get it to check that. You might need to get the calculator to redraw it once you switch it over to that dot mode. If you just go back to y equals and you change one little thing about your equation, even if you just retype the same number, then when you go back to the graph, then it will redraw it. And so it would typically then redraw it without that line in there once you switched it to the dot mode. Look at page 54. Page 54, they talk to us about families of functions. It says to understand how the expression for a function relates to its graph, it's helpful to actually graph a family of functions. That is, a collection of functions whose equations are related. And the example that they give us is y equals x cubed plus cx, where we're going to go through and we're going to change c to various values. So like they start off by putting 2 in for c, so you'll see there x cubed plus 2x, and then they put in 1, x cubed plus 1x, and then they put in 0, x cubed, and then they put in -1, so x cubed minus x, and x cubed minus 2x, and x cubed minus 3x, and they go through and they graph all of those there for you in the middle of page 54. You'll notice that they have the same basic shape. You know, they start down and they end up and they have curves in between. But you can see how changing that one value changes the graph of that function. And that's the idea of a family of functions. All right, look at example 9. Example 9 says, find the solution of the equation cosine x is equal to x, correct to 2 decimal places. Now, I know it says 2, but we're always going to use 3 just as our standard for AP. So we don't want to round off any less than 3. We can maintain more than that, but round off to at least 3. So a couple of ways that we learned last year to do this. We haven't seen it yet this year. So if I want to know where cosine x is equal to x on my calculator, how could I do that? Okay, I could graph the two of them and find their intersection. So how am I going to graph the two of them? I'm going to take what's in the left-hand side and put it in y1. And I'm going to take what's in the right-hand side and put it in y2. And then, yes, I am looking for their intersection. So I'm still going to be in radian mode. Since I'm doing trig stuff, then I might choose zoom 7, which is zoom trig, to set the window for me. So there, of course, is the graph of our normal cosine curve. Hasn't been altered at all. And there's the graph of the line y is equal to x. So if I'm looking for where they're equal to each other, as you told me, it's just their point of intersection. So I can get my calculator to find that for me. So second trace, which is my calculate menu. I'm going to choose option number 5. And notice that it will automatically go to what I have in y1 and ask me, do you want me to use that for the first curve? And I'll tell it enter for yes. And then it switches and says, do you want us to use what you have in y2 for the second curve? And again, I can tell it enter for yes. And then I'm going to go give a guess. So come to about where I think that point of intersection is and hit enter. And then it will tell me that precise point of intersection. So again, that was second trace. We chose option number 5. Enter to tell it yes for first curve, enter to tell it yes for second curve, enter our guess, and it will tell me that point of intersection. So we're looking for the x value, right? It's solve for x. So we're going to get x is equal to 0.739. X is equal to 0.739. All right, here's the other way that we did that exact same type of thing last year. Remember that solution, x-intercept, 0, root, all synonymous terms. So the other thing that I could do is I could go to y equals. I'm going to turn these off for a second. I could go to y equals and I could move that whole equation over to one hand side set equal to 0. So I'm going to move it all over to the left hand side. So I'm going to say cosine x minus x. So cosine x minus x. And we're still on that zoom trig. So there's what my graph would look like. What am I looking for here? What does the solution look like on a graph? The x-intercept, yes. So I can go to, again, my calculate menu, solution, x-intercept, 0, root, mean the same thing, right? So I can choose 0. I think that my 0, my x-intercept, my solution, my root is about right here, so I'll go a little bit to the left and give the left boundary that it's asking for. Go a little bit to the right and give the right boundary that it's asking for, and then go back and give the guess, and you'll notice that it gives me the exact same x value, 0.739. So it doesn't matter which way we do that. All right, one last example from the handout that I wanted to show you of lies my calculator told me. If we take 10 to the 15th and we add 7.2 to that, and then we subtract 10 to the 15th, what should that give me thus far? Yeah, I should have 7.2. Let me back up and move that parenthesis. So right now I should have 7.2. Let's multiply that by 100. So what should I get for my answer? 7.2 times 100. 720. Is 0. Because that's what my calculator said, and my calculator is always right. I must have typed it in wrong. No, we typed it in right. Lies, my calculator told me. So the idea here is your calculator can only maintain a certain number of decimal places. So what happens is when it gets 10 to the 15th up here, that's such a huge number that when we add the 7.2, it just has to round that off to maintain the number of decimal places it can. So it rounds that off, and then it subtracts, it loses the 7.2, and then it subtracts the 10 to the 15th, and so it thinks it just has 0. And 0 times anything would be 0, right? And so that's why we're getting 0 as an answer. Okay? So again, that handout comes from AP of things to watch out for, of ways your calculator can mislead you that we want to help you with. So we definitely want to pay careful attention to that. Okay, so for our homework tonight on page 55, it's right over here on the board. 3 through 35, every other odd, challenge 25. Page 55, 3 through 35, every other odd, challenge 25. Now, on numbers 7 through 19, it literally says graph it on your calculator. So all that I need for you to do is give me a rough sketch of the graph that's on your calculator screen on your paper so that I can see that you did it.